This video will teach us how to use a Dean Stark to obtain an ester. The Dean Stark is a device consisting of a burette with a stopcock, a reflux refrigerator at the top, and a side tube to which a reaction flask is connected. It is used for the elimination of water produced in a chemical reaction by azeotropic distillation. To obtain the ethyl chloroacetate ester, we will need chloroacetic acid. I chose to obtain chloroacetic acid with a mineral acid and sodium chloroacetate because I didn't have chloroacetic acid. In a beaker, put 30 ml of water and 25 ml of concentrated hydrochloric acid. Stir it, add 30 grams of sodium chloroacetate, and heat it slightly until it completely dissolves. Cool with an ice bath and saturate with sodium chloride. Extract the chloroacetic acid 3 times using 30 ml of ether. Separate the organic layers in a separating funnel. Dry the organic solution with anhydrous magnesium sulfate until it becomes transparent. Evaporate the ether using a rotary evaporator after filtering it. Transfer the results to a 50 ml beaker. Leave in the oven at 60 degrees for a day to eliminate all the residual ether and store in a refrigerator so that the chloroacetic acid crystallizes. Once crystallized, we will obtain the ethyl chloroacetate ester. To obtain the ethyl chloroacetate ester, we will use chloroacetic acid, ethanol and concentrated sulfuric acid like catalyst. The solvent to remove water in the Dean Stark equipment will be toluene. In a 250 ml flask, we put a solution of 18.8 grams of chloroacetic acid in 40 ml of 96% ethanol. Slowly add 1 ml of concentrated sulfuric acid with a stir. Assemble the Dean Stark equipment and fill it with 60 ml of pure toluene. Place a reflux coolant on the top of the Dean Stark equipment. Boil for 2 hours. Toluene is less dense than water. The condensed vapor is formed by an azeotropic mixture of toluene and water that falls into the Dean Stark, forming 2 layers and separating the water that is denser from the toluene. In Dean Stark's burette, we can observe the separation of water from the reaction and eliminate the water by opening the stopcock with caution. The amount of water obtained in this operation was less than what was expected. After 2 hours, we let it cool and neutralize it twice with 40 ml of saturated sodium hydrogen carbonate solution. We must observe that no carbon dioxide is produced and the aqueous layer does not give an acid reaction with the pH indicator paper. In a separating funnel, separate the organic layer from the aqueous layer. After drying the result with anhydrous calcium chloride, allow it to rest for 12 hours. To eliminate toluene, we distill the result in distillation equipment with a packed column. At a temperature of 110 to 120 degrees, distill the fraction that is primarily composed of toluene. Remove the packing column and continue distilling, collecting the portion that distills between 140 and 145 degrees after most of the toluene has been distilled. The yield was 6.32 grams, a very low yield for the material used in the operation. I needed a large amount of ethyl chloroacetate and decided to obtain it by the traditional route, Fischer esterification. For 4 hours, I heated a mixture of 32.2 grams of chloroacetic acid diluted in 40 ml of ethanol and 5 ml of concentrated sulfuric acid at reflux in a 250 ml flask. After 4 hours of reflux, let it cool and neutralize the result twice with saturated sodium hydrogen carbonate solution. I separated the organic layer with a separatory funnel and the organic layer was dried with calcium chloride. After distilling the final product, I obtained 24 grams of ethyl chloroacetic ester, a 57% yield.